In the second module, we're going to look at an example of Monte Carlo valuation in a little more detail and understand why it works a little bit better. So we begin with this computing an option price as a discounted expected value. We're actually going to assume that we have a distribution 1 year from now, and that we're going to develop this distribution in step sizes of 1/3 of a year. So we'll have 3 steps to maturity of this option. So we have 4 stock prices at that time, and we can take an expectation using the binomial probabilities and the associated P star. In essence, what we're doing is discounting the average payoff, and we're discounting it with the risk-free rate. And in our binomial model, we would just use this formula, which is from the author's slide, but I wanted to repeat it only because, in general, there are 2 ways of representing the summations that appear in these binomial formulas. And I and the author tend to order our summations a little bit differently. Notice that the author's summation, I equals 0, corresponds to the highest stock price. And as you go from I equals 0 to n, the stock price goes from the highest to the lowest. And in my earlier formula, I ordered the stock prices so that I equals 0 is the lowest stock price, and it goes up. Obviously, it makes no difference which way you ordered the sum, but I wanted to point out that you could see this formula either way. What's important is that the exponent of P star is the same as the exponent of U, because that's the probability of getting a U, and the exponent of P is the same as the exponent of D. Sorry, the exponent of 1 minus P star is the same as the exponent of D, and that the sum of those exponents is always the constant n. And then it doesn't really matter whether the summation orders from the lowest to the highest stock price or from the highest to the lowest stock price. And of course, the binomial, this coefficient is symmetric in n and n minus I. So here's a lattice where I have a $40 initial stock price, 30% vol, 8% risk-free rate. I have a 1-year time horizon and a 1/3 of a year time step, and no dividends. So I have a P star, which we can calculate using the usual U and D formulas. We're using the Chapter 10, the more common version of the U and D formulas, and the P star comes out to about 0.4568. And we then develop our lattice. You can see we then have our 4 stock prices, each of which implies a payoff, multiplying the payoff by the probabilities, and then we simply add them up and do a present value. So the expected value is $7, and right down here you can see it, $7.66. And when we do the present valuing, a 1-year discount at 8%, we get to $7.074. So that's our option price for this call option. But the expected value of the payoff is around $7.66, and then the present valuing brings it to about $7.07. So if we wanted to now compute this price as a discounted average value, so again, we're going to assume a stock price distribution 1 year from now, just to be consistent. And we're going to sample stock prices from the distribution. We have a binomial distribution which provides only a choice of 4 different stock prices. The probabilities of those 4 different stock prices are observed in the earlier slide. There's a 9.5% probability of the highest price, a 34% probability of the next highest, and so forth. So we have 4 different probabilities, 4 different stock prices. We generate a large number of stocks with given that probability structure. and we evaluate the call option on each stock price and take an average. Of course, the goal would be to get an average close to the theoretical average of the 766. So using the notation I introduced earlier, the stock prices, the fact that they're random, a random sample, means that the probability that any given randomly generated stock price equals one of the lattice prices is the corresponding probability on the lattice of that price. That's exactly what it means. And so from a sample of size n, if ni, using my earlier notation, is the number of that sample that equal that particular stock price, the expected value is exactly equal to this. That's the multinomial distribution. That the expected number of stocks, stock prices that equals the ith price on my lattice is exactly equal to the sample size times the probability of that, that price occurring. So you can see then the formula collapses quite neatly, namely that the estimated price is here. And then if I look at an expected value, I made the argument earlier that ni over n is approximately equal to the correct probability. But we can say more. It's not only approximately equal to, but if I take the expected value of this Monte Carlo price, because the expected value of every ni is n times the correct probability, you see the n's cancel out, and I get CT. So what we have is that there are many ways of deriving this result, but the expected value of the Monte Carlo price is the lattice price.